Subrahmanyan, Chandrasekhar's 1929 paper, The Highly Collapsed Configurations of a Stellar Mass, stands as a pivotal work in astrophysics, marking an early foray into the theoretical understanding of white dwarf stars and ultimately foreshadowing the existence of black holes. Its genesis lies in the burgeoning field of quantum mechanics and its application to stellar structure, a field riddled with paradoxes that Chandrasekhar sought to resolve. Before Chandrasekhar, the understanding of stellar evolution faced a critical impasse. Arthur Eddington, a leading astrophysicist of the time, championed the understanding of stars as giant spheres of gas held in hydrostatic equilibrium, the outward radiation pressure balancing the inward force of gravity. Eddington's work, particularly his mass-luminosity relationship, successfully explained the behavior of main sequence stars. However, towards the end of a star's life, when nuclear fuel depletes, the core begins to contract. Eddington, among others, struggled to explain the final fate of such stars. He famously resisted the idea of complete gravitational collapse, a scenario that appeared to violate fundamental physical principles as understood at the time. Ralph H. Fowler's application of Fermi-Dirac statistics to dense matter provided a crucial stepping stone. In 1926, Fowler demonstrated that at extremely high densities, electrons would be forced into high-energy states, creating a degeneracy pressure that would resist further compression. This degeneracy pressure, arising purely from quantum mechanical effects, offered a possible mechanism to hold stellar collapse and stabilize a star as a white dwarf. Fowler's theory provided a plausible explanation for the observed properties of white dwarfs, such as their small size and high density. Chandrasekhar, building directly upon Fowler's work, introduced relativistic effects into the equation. He recognized that as the density of a white dwarf increases, the electron's velocities approach the speed of light, rendering a Newtonian treatment inadequate. In highly collapsed configurations of a stellar mass, Chandrasekhar meticulously derived the equation of state for relativistic degenerate electron gas. This involved calculating the pressure exerted by electrons whose momentum is comparable to or approaches mc, where m represents the mass of the electron and c represents the speed of. The key result of Chandrasekhar's calculation was the discovery of a limiting mass, now known as the Chandrasekhar limit. This limit, approximately 1.44 solar masses for a non-rotating star supported primarily by electron degeneracy pressure, represents the maximum mass that a white dwarf can possess. If a star's core exceeds this limit after exhausting its nuclear fuel, electron degeneracy pressure proves insufficient to counteract gravity, leading to further collapse. The derivation itself involved solving the equation of hydrostatic equilibrium, which balances the inward gravitational force with the outward pressure gradient. Chandrasekhar implemented the relativistic equation of state for the degenerate electron gas. This resulted in a polytropic equation of state of the form pressure is proportional to density to the power of gamma, where gamma equals 4/3 in the relativistic case. Solving the Lane-Imden equation with this polytropic index, Chandrasekhar obtained a family of solutions describing the structure of white dwarfs. However, he discovered that these cease to exist by a certain mass, revealing the existence of the limiting. The immediate impact of Chandrasekhar's work was met with considerable skepticism, most notably from Eddington. Eddington found the implication that stars exceeding the Chandrasekhar limit would inevitably collapse to a singularity deeply unsettling. He viewed it as an absurdity, a breakdown of the laws of physics as he understood them. Eddington publicly challenged Chandrasekhar's calculations and interpretations, arguing that some unknown mechanism must prevent complete collapse. His objections, rooted in a preference for established Newtonian physics and a resistance to the more radical implications of general relativity and quantum mechanics, significantly delayed the widespread acceptance of Chandrasekhar's findings. Despite Eddington's opposition, Chandrasekhar's work gradually gained recognition and acceptance within the broader astrophysics community. Astronomers, facing mounting observational evidence of stars with highly unusual properties, realized the importance of Chandrasekhar's theoretical framework. The existence of neutron stars, predicted by Walter Baade and Fritz Zwicky in 1934, provided further support for the possibility of stellar remnants far denser than white dwarfs. The development of general relativity, particularly the solutions for black holes derived by Carl Schwarzschild and later refined by others, ultimately cemented the understanding that sufficiently massive stars could indeed collapse to form singularities. Chandrasekhar's work indirectly influenced the development of stellar evolution theory. His calculation of the limiting mass provided a critical benchmark for understanding the final stages of a star's life. Specifically, stars above the Chandrasekhar limit could proceed to become neutron stars or black holes. Furthermore, Chandrasekhar's meticulous mathematical approach and his insistence on applying fundamental physical principles rigorously set a high standard for theoretical astrophysics. His work profoundly influenced subsequent generations of astrophysicists, inspiring them to tackle complex problems with mathematical precision and physical intuition. The intellectual lineage leading to Chandrasekhar's 1929 paper includes several key figures. As previously stated, Faller's application of Fermi-Dirac statistics to white dwarfs provided the essential foundation. However, the contributions of people like Sommerfeld, who developed the free electron model of metals, were also important, as this model provided a simpler context for understanding electron degeneracy. Chandrasekhar himself was deeply influenced by Eddington's work on stellar structure, even though he ultimately challenged Eddington's resistance to the idea of gravitational collapse. The influence of Chandrasekhar's work on others is equally profound. His calculation of the limiting mass directly influenced the research of people like Robert Oppenheimer and George Volkoff, who in 1939 calculated the maximum mass of a neutron star, now known as the Thom-Oppenheimer-Volkoff limit. This work, in turn, paved the way for the theoretical understanding of black holes. Chandrasekhar's work inspired many theoretical astrophysicists, including Kip Thorne and Stephen Hawking. The critiques of Chandrasekhar's work, levelled primarily by Eddington, stemmed from a combination of factors. Eddington, a staunch advocate of classical physics, struggled to accept the implications of quantum mechanics and general relativity, particularly the idea of a singularity. He argued that the physics at extremely high densities and gravitational fields was poorly understood, and that some unknown mechanism must prevent complete collapse. Eddington's objections were also fueled by a degree of scientific rivalry. Chandrasekhar, a young Indian physicist, was challenging the established authority of a senior British scientist. This added an unfortunate layer of personal tension to the scientific debate. Over time, the accumulation of observational evidence and theoretical advancements has rendered Eddington's objections untenable. The discovery of pulsars, identified as rapidly rotating neutron stars, provided direct confirmation of the existence of stellar remnants far denser than white dwarfs. The development of general relativity and the recognition that black holes are a natural consequence of Einstein's field equations further solidify the understanding of gravitational collapse. Today, Chandrasekhar's work is universally recognized as a cornerstone of modern astrophysics, and his calculation of the limiting mass stands as one of the most important results in stellar evolution theory. Eddington's initial resistance, now viewed with a certain historical irony, serves as a cautionary tale about the importance of embracing new ideas, even when they challenge established paradigms. It is a valuable reminder that scientific progress often involves overcoming ingrained biases and preconceived notions. In summary, Subrahmanyan Chandrasekhar's 1929 paper, The Highly Collapsed Configurations of a Stellar Mass, represents a landmark achievement in astrophysics. Building upon the foundation laid by Fowler and others and incorporating relativistic effects, he calculated the limiting mass for white dwarf stars, revealing the inevitable gravitational collapse of more massive stellar cores. While initially met with skepticism, Chandrasekhar's work ultimately revolutionized the understanding of stellar evolution, paving the way for the discovery of neutron stars and black holes. His rigorous mathematical approach and his unwavering commitment to fundamental physical principles continue to inspire astrophysicists to this day. His legacy endures, not only in the specific results he obtained, but also in the broader influence he exerted on the development of theoretical astrophysics as a whole.